Okay, we're going to make electrolytic, or not electrolytic, electrochemical cells tomorrow in class. And there are two types of electrochemical cells. There are electrochemical cells that happen where the reaction occurs, and there are ones where they don't occur. So the words we used to describe when a reaction happens and when it doesn't, back in thermodynamics, were spontaneous or non-spontaneous. Has nothing to do with the speed, it just means this is favorable, this will happen. A ball will roll down a hill, the ball will not just roll up a hill spontaneously. So we are going to make spontaneous cells in class. So these are cells where the reaction is favored. So we're going to have positive voltage. And we call these cells galvanic or voltaic. It's the same thing, different name, same thing. If we were making non-spontaneous, we'd call them electrolytic, but we'll see those later. Okay, so our cells that are going to have positive voltage, meaning the electrons are going to move to be more stable. We're going to have, our electrochemical cells will have one area that's being oxidized, so electrons are leaving that one area and in one cell, and they're going to another area, so they're reducing something else somewhere in another cell that'll be connected. And since the electrons are moving from one side to another, we'll need something that'll complete the circuit. So here are your parts. There's a lot of vocabulary. You want to be able to draw the diagram, label the parts, and know what every part does. So I'll give you the names, then we'll look at the cell. I'll tell you what they are as I'm making the cell. And if you forget, you can go back, because this is a video, therefore it can be rewound. Yes. So parts we need. That salt bridge is the thing that completes the circuit. So as one side is oxidized, the other side is reduced, the electrons would stop moving if we didn't complete the circuit and move something negative from this side over to here. So the salt bridge is actually going to kind of counter that charge to keep both of your electrodes neutral. And it's usually full of something unreactive. We'll use potassium nitrate pretty much every time. The next, we have our electrodes. The electrodes are going to be the two metals that are in contact with the solutions. Sometimes they undergo oxidation if they're more easily oxidized than anything else present. The two electrodes are either going to be a cathode or an anode. So the electrode that is the cathode is the positive electrode where reduction occurs. So in my class, we remember red cats are positive. And it's just a way to try to keep it straight. These systems are kind of big, there's movement going on. If your electrons are going one way, then we're naming this your cathode and this is your anode, and then you have reduction here and oxidation here, but if your electrons change direction, you change the name of everything. So to keep it straight, I have my students label the cathode first. So like, where is the reduction occurring? At the cathode. So my electrons are going here, that's my cathode, that is positive. The rest I can figure out if I just have that one point. The anode is going to be the negative electrode, and that's where the oxidation is occurring. You have to be able to figure out the electron flow. So the electrons are going to the thing that is being reduced. So going to the metal ion that's being reduced, for example. And you'll want to label your ionic solutions. That's going to be your little positive ions floating around in contact with the metal electrodes. Those positive ions are often what gets reduced. Not always, but often. Okay, so let's make our galvanic or voltaic, whatever you fancy, cell. I'm going to make it with zinc and copper, but I'm just going to start drawing my cell, label the parts, and then I'm going to figure out where the electrons would go. It's okay if I draw it so my electrons go this way or so that they go that way. It doesn't matter which direction they're going as long as you label it. So here we go. I have two beakers. These beakers are going to contain ionic solutions. Those solutions are going to be in contact with my electrodes, which are pieces of metal, right? This is beautiful art. Piece of metal. The metals are connected with a wire so that the electrons can go from one side to the other, or vice versa. And let's see, I'm going to make this my zinc metal, so Zn, and this will be zinc 2+ ion floating around. My other option, I have copper metal and copper 1+ ion, so Cu and Cu+. Your teacher might want you to label the whole solution, so like, call that zinc nitrate or zinc chloride. Got a sneeze that just isn't coming. And then I need to add a salt bridge. So that way if all the electrons are going this way, I need something to take the negative charge back. Or if all the electrons are going this way, something to take the negative charge back. So I'll put in my salt bridge, which is just something that contains a bunch of ions that can move freely. And I'm going to put in some potassium, and I'm going to use nitrate, and O3, 1 minus. Later I'll figure out whether the potassium goes this way or that way. Okay. Actually, by later, I mean now. So on my sheet that I get for the AP chemistry test, it gives me the standard reduction potentials, and they're written like this. Zn 2 plus 2 electrons goes to zinc metal, and there's a value beside that that is a negative 0.76 volts. Okay, so that means when electrons go from a hydrogen cell to zinc ion, it's an unfavored move by 0.76 volts. I also have copper 1 plus 1 electron going to copper, and this guy is written as a positive 0.52 volts. Alright, so since I'm making a galvanic cell, I need a positive potential overall. So I can see that this move was an unfavored move. Adding the electrons to the zinc was unfavored, but adding the electrons to the copper was favored. This is pretty easy for me to figure out which one to flip. I'm going to flip the top one. And whenever I flip a reaction, I know I'm going to use the opposite sign. So now I'll just write zinc goes to Zn2 plus 2 electrons, and now this is going to be favored by 0.76 volts. Okay. Alright, so all in all, this whole thing is favored by a positive 1.28 volts. Sure you can't read that. So I can see that zinc is losing electrons, right? Because it starts off as this whole metal atom, and it ends up as a metal ion that doesn't have its electrons there. So I'm going to draw the electrons going away from the zinc. Electrons going this way. And I can see that copper ions are gaining electrons. So these electrons travel in the wire, they hit this copper piece of metal, go down to the bottom, and now they're negative, so they attract one of these positive ions towards it. The positive ion takes on the electron. It's no longer an ion. It is now a piece of copper. So this electrode actually ends up getting bigger as copper ions become deposited and become reduced into copper metal on the electrode. So it just gets bigger and bigger and bigger. Meanwhile, this guy's going to get smaller and smaller because a zinc atom will lose 2 electrons and become a zinc ion floating around. So this concentration is getting higher, but the metal's getting smaller. Okay? Like taking little bites out of that metal. So if these negative electrons are going this way, this is where reduction is occurring. Red cats are positive. Reduction is over here. So this is where reduction occurs. So that means the Cu1 plus gains an electron to become copper. Sometimes you're asked to write the half reaction at each electrode. And it's going to be, red cats are positive, this is going to be a positive electrode. That means that this is going to be where the oxidation occurs. It's going to be your negative, right? And this is the anode. This is my cathode. Over here, the copper is my cathode. If I'm asked to label the charge of each electrode, that's when they're asking me to put a positive on the copper and a negative on the zinc. The only thing I haven't shown is the flow of the ions in the salt bridge. Since the negative electrons are going over here, they're gonna repel these negative polyatomic ions, these negative nitrates over the other way. And meanwhile, these positive potassium ions are going to be attracted to where the electrons are going. And that is that. Okay. So make sure you can label the parts, you figure out where the electrons are going, why do we have each part.